So today we're going to be talking about experiment 2, which is infrared spectroscopy. It's also known as IR spectroscopy, and you're frequently going to hear it referred to as IR spectroscopy simply because that's a shorter thing to say than infrared. But nonetheless, we're going to talk about the idea of identifying functional groups in molecules, and IR is a very good technique that allows us to identify the functional groups very easily using this technique. Before coming to lab, you really need to review Chapter 2 in your lecture text in the Solomon's text. It covers functional groups, polarity, and it also covers infrared spectroscopy. So you need to read that in addition to Experiment 2 in the lab text. So let's look at an IR model, and what I've got drawn here is an example of a diatomic molecule. Of course, most organic molecules are more complicated than this, but this shows what's going on. Typically, when we look at a molecule, we draw two different atoms. In this case, I'm using a red atom and a green atom. They can be anything, but they are different, and they're joined, of course, by sharing two electrons in this black bond. Now, this model is not realistic. Molecules are not static. They vibrate. And it turns out that you can put energy in the form of IR radiation and actually stretch that bond to be longer. And we can detect this using an IR spectrometer if, and only if, this results in a change in dipole moment. Okay, so if we get a change in the dipole moment, we can actually observe this by infrared spectroscopy. So what do I mean by a dipole moment? Well, let's suppose that the red atom is less electronegative than the green atom. So the green is more electronegative, say something like fluorine, and the red atom is something less electronegative, something like perhaps hydrogen. And so we can draw this as being a polar covalent bond where the red atom takes on a partial positive charge, the green atom takes on a partial negative charge, and what we have here then is a dipole going in this direction. And dipoles are vectors. They have magnitude and they have direction. And so we draw the vector like this, going towards the negative part. You're going to learn more about vectors and vector math when you get into physical chemistry and take your physics, but for right now, you just need to know that the dipole is going in the direction as drawn. However, upon absorbing energy in these two atoms stretching, again, partial positive for the red atom, partial negative for the green atom, but now the dipole is stretched. And so the magnitude of the dipole is larger, and we have a change in the net dipole moment. Okay? The reason that this happens is the green atom, being more electronegative, is pulling the electrons to it. And as it stretches, it's pulling more electrons to it, and that stretches out that dipole. And if we have a change in the dipole moment, we can observe this by IR spectroscopy. However, one can imagine a situation where we have two green atoms connected together. Let me erase this up here from the top so we can see a little better. Okay. And in this case, we notice that both of them are electronegative, pulling electrons to themselves, and the dipole moment in this direction is canceled by the dipole moment in that direction. So even if that bond stretches, there's still the dipole going to the right and the dipole going to the left perfectly cancel one another, and there's no net change in dipole moment. In a situation like this, we could not observe this by IR spectroscopy. So that's kind of in a nutshell how IR spectroscopy works. So we've got to have that change in dipole moment, and we can observe the absorption of the IR energy using an instrument known as an IR spectrometer. Okay. Fortunately for organic chemists, it turns out that all functional groups that we're interested in anyway, when stretched, will result in a net change in dipole moment, and so we can actually observe these by IR quite easily. And so this is a very nice technique for observing and identifying functional groups in an organic molecule. Fairly straightforward manner you're going to learn about in lab. What you're going to see from a practical standpoint when you take an IR spectrum, you're going to get a graph, basically a chart from the computer. On the x-axis, you're going to have wave number. is in centimeters to the -1, or reciprocal centimeters. We call that the wave number, and basically that's the wavelength of energy, the infrared energy that's being absorbed or transmitted. And on the y-axis, typically we observe this as percent transmittance, how much of the energy is making it through the molecule to the detector. Now, when you get this graph, you're going to see a lot of information on that, but you need to break it down into simple things. So this typically goes from about 4,000 reciprocal centimeters to about 400 reciprocal centimeters, so it's a pretty large scale. And what you need to do is identify 1,500. And take your paper and draw a line, either imaginary or real, with a pencil at 1,500. Everything to the right of 1,500 is what we call the fingerprint region. This is a very complicated region, and it is unique for each molecule, hence the name fingerprint region. It is not very useful in terms of identifying functional groups, and so most organic chemists ignore the fingerprint region. When you get into higher level chemistry, such as advanced inorganic chemistry and stuff, the fingerprint region will become important. But for our purposes, we're going to ignore it. But this is where you're going to find things like carbon-carbon single bonds and those types of complex stretching that occurs in that region. Now, once you've identified 1,500, everything for functional groups is to the left. So between 1,500 and 4,000, that's where we're going to do all of our focusing. And all you need to do is go out 500 wave numbers. So from 1,500 to 2,000, and we're going to draw another imaginary line. And again, you can actually write this out on your graph if you wish, or your spectrum when you get that printed out of the computer. But between 1,500 and 2,000 is what we call the sp2 region. So anything that's sp2 hybridized, this is where you're going to find that. Okay? And this is going to be like carbon-oxygen double bonds. There's a lot of functional groups that contain the carbonyl, of course. So you're going to find those in these regions. You'll also find carbon-nitrogen double bonds, for example, and you'll find carbon-carbon double bonds. Those will always appear between 1,500 and 2,000 in this narrow region of the IR spectrum. Now we're going to move out another 500 to 2,500. And of course, my scale here is a bit exaggerated, but you'll be able to see this on your spectrum very, very easily. This is the SP region. So between 2,000 and 2,500, anything that's SP hybridized, that's where we're going to find it. And so this is going to be things like carbon-carbon triple bonds. We'll find that carbon-carbon triple bond stretch there. We'll also find carbon-nitrogen triple bonds there. So for the nitrile functional group, you'll always find that in that region. And you can find the carbon-oxygen double bond of carbon dioxide there because carbon is sp hybridized. Okay? So this is the sp2 region. This is the sp region. This region between 2,500 and 4,000 is known as the hydrogen region. This is where you're going to find things like carbon-hydrogen bonds stretching. This is where you're going to find OH bonds for alcohols or carboxylic acids. And it's also where you'll find the NH stretch in amines and amides. You will find those in this region very, very quickly. So if you get your IR spectrum, print it out, look at it, 1,500, 2,000, 2,500, make lines there, all of a sudden you know a lot of information. If you see something stretching in here, if you see peaks appearing in this region, you know you've got something that's sp2 hybridized. You may not know right off the bat whether it's a carbon-oxygen double bond or a carbon-carbon double bond, but there are tables in your book that will allow you to pinpoint where a carbon-carbon double bond comes or where a carbon-oxygen double bond comes. And those tables are table 2.1 in the lab manual and table 2.7 in your lecture text, in the Solomon's lecture text. You need to have both of these tables not memorized, but at the ready, so to speak, so that you can look up specific values for this. Okay? So let's talk about some common stretches. I'll go ahead and erase this real quick. We'll talk about some common stretches that you need to know and really commit to memory because they appear so often on exams and in organic chemistry that it's really helpful to commit these to memory. The carbon-oxygen double stretch, again, that's going to appear in that sp2 region. It tends to be very strong. Meaning that if you're looking at percent transmittance, it's going to go almost all the way down to the baseline. So if this was the graph that we were looking at, there would be my 1500 to 2000. A C double bond O tends to be quite strong in its stretching ability. This would have looked something like that. OH stretches are also quite characteristic for alcohols and for carboxylic acids. The OH stretch for an alcohol is going to be around 3,300 wave numbers. So it's going to be over in this region. Okay? But it's going to appear for an alcohol, it's going to appear as broad and strong. It's going to appear symmetrical. It's going to appear something like that. However, if it's an OH for a carboxylic acid, going to appear broader, and it's going to stretch all the way over into the CH stretching region. And so by simply looking at the IR spectrum, you could determine whether or not you're going to have an alcohol or a carboxylic acid fairly easily. However, for a carboxylic acid, not only will you see this type of stretch, but remember a carboxylic acid has this general structure. So you've got a carbonyl, so you should see something between 1500 and 2000. And then you'll also see the OH, which will appear something like this in the hydrogen region. Let's look at an example spectrum.